Hi, Tyler.
How's it going?
Good. You?
Doing pretty good.
Good. Glad to hear it. Have a good weekend.
Oh, yeah. It wasn't nearly as productive as I would have liked, but yeah. That's
Yeah,
sometimes.
I know the feeling. Sometimes that happens. Hey, Lyle. How you doing?
I'm good. I have a question, but we might want to wait for more people to get here.
All right. Yeah. All right. Go ahead with it, and we can repeat it when folks show up.
Yeah. Well, I may be the only one with this problem too. So you gave us a relationship last time for the gamma matrices. In particular, you gave us the anti-commutator relationship of the gamma matrices, and it's equal to 2 times the metric times an identity, or metric components times an identity.
That's right.
So
well said.
My question is, you also told us that the dimensionality of the gamma matrices is 2 to the 2 over n by 2 to the 2 over n. They're square matrices.
N over 2, 2 to the n over 2.
Yeah. So what I've been struggling with, let's just take a dimension of like 10 dimensions, because I think you had mentioned a 10-dimension example, right?
Yeah, that's where superstrings live. So
right, you were trying to illustrate how complicated they could get, how large the matrices could get, and I think it was 32 by 32.
Yeah, that's what it works. Yeah.
Okay.
Yeah, that's right.
I'm good with that. So on the left-hand side of the equation, which is where you would expand the anti-commutator, you're going to have a 32 by 32 matrix times a 32 by 32 plus 32 by 32 times 32 by 32.
That's right. Yeah.
Now, when you work all that out, what you're going to be left with on that side of the equation is still a 32 by 32 matrix, correct? Because when you
right.
Yeah. Okay. So on the right-hand side of the equation, though, the metric is just 10-dimensional. So do we not have a disbalance in the dimensionality of the two sides?
It's the identity. The identity will be big. Here, let's write it out. Okay. So hey, Kevin, Alex, Guillermo, good to see you. We were just prepping me on a question that Lyle has, and it's about the dimensionality of the Clifford algebra and the various elements of the Clifford algebra. So let's imagine we're in some larger dimension where these things are really big. It's this thing that's 2 to the n over 2 by 2 to the n over 2. All right, these indices run from 1 to 10. These tell you how many gamma matrices you have. So we've got A equals 1 up to the dimension. Let's just say 10 for concreteness. And but then this thing is some matrix AB, where A and B run from 1 all the way up to 2 to the n over 2. All right, in this case, 32. So so you have 10 32 by 32 matrices in 10 dimensions. So this is the 10-dimensional metric. And this tells you, okay, you choose which matrix here, you choose which 32 by 32 matrix here, and you're either going to get 0 or plus or minus 1 times the identity matrix here. So this identity is, we can write it as Kronecker AB in those indices. If we put indices in here, we have gamma A is a 32 by 32. Gamma B is some other 32 by 32. Let's see, so this is going to be BC, product symmetrized on BC, basically. Or no, wait a minute, no. Better write it out. So the other way around, gamma B A, B, gamma A, B, C plus. So there's the anti-commutator very explicitly. So we have a pretty good number of really big matrices. Yeah. So yeah, often, these things can get pretty confusing because you're working in several spaces at once. And what I do at several places, say in the quantum field theory book, is I will expand everything and put in explicit indices this way, just to be sure that I really understand what's happening. Frequently in field theory, for example, you are going to see a term in an action that'll look like psi bar, say gamma A, or all right. Here, this is an electromagnetic coupling of a spinner to the vector potential. This slash is shorthand notation for a sum of a gamma matrix with any vector. And if I haven't mentioned that already, I'll probably mention it again. But we call that A slash. This psi bar.
Dirac delta be AC instead of AB?
Sorry,
Dirac delta. Why is it AB, capital AB?
Your top
instead of
line
AC?
on the right. It should be
Dirac.
AC.
I'm lost.
You'll sum over the B's and you'll have an A to C index.
I'm summing here, I get AC here, sum over B, I get AC there, but I've interchanged the ABs to do the anti-commutation.
Look at the right side of that equation.
Here.
Yeah, look at the delta, or Dirac.
Oh, that's not a Dirac delta, that's a Kronecker.
I'm sorry,
That's
Kronecker.
a 32 by 32 identity matrix.
Sure, but the index is because you summed over the B. Yeah.
Should be C.
Yeah,
You're right.
good.
You're right. Absolutely. Yeah, good. Yeah, the equation evolved as I was writing it. Yeah. Okay. So this means psi dagger and typically gamma 0, and then we have a psi here. And you'll see this, this kind of shorthand all the time in field theory stuff. But this is a cheat, okay? Because all of the gammas have, they're basically transformation matrices. They have one index up and one index down. They're 1-1 tensors of some sort. But if you try to write that, okay, you've got a vector here, call it psi A. You've got some linear combination of gamma matrices acting on those. Then what you're supposed to have here, this psi bar, really should be a down index, but it's not. All right, this gamma 0 is a transformation. CD psi dagger D. What you actually have here is something like this, or in the other order. Maybe it's psi dagger D gamma 0. It's not a transpose, but you could write. Well, let's see. What do we need here? We need a B down, but we've got something up. It's wrong. What really goes there in place of gamma 0 is a metric. There's some Hermitian metric on this spinor space. So in my notes, I've identified that explicitly as HAB. And then if you write this, I can write this expression out as psi dagger A HAB, a mu gamma mu B C psi B. So it works. Now, what happens is you usually just choose a convenient basis set of gamma matrices. So I choose 4 matrices. Now hold them fixed. And in that basis, I identify the components of gamma 0. This is obviously a basis-dependent relation. So in my chosen basis, I can set the components of H equal to the components of gamma 0. This is what's being done when you see expressions like that. Properly speaking, that what goes here really needs to be some inner product of the spinor space. So I've tried to make that explicit, through our text, and you won't see it in much of the literature. I don't think anybody does that in field theory. Relativists are going to miss the metric, but field theorists, gamma 0. So it's a, what do they call it? Like an abusive notation, but it works. Your basic, you know what that matrix is. All right, it's 1, 1, -1, -1, or whatever basis you've chosen. As an exercise, I don't know how many of you have done this yet, but I've asked you to show that once you have a set of gammas that works, then any complex general linear GLNC transformation, similarity transformation of those matrices also works. An easy exercise, just substitute in and it'll work out. Okay, so probably answers the question. I hope that answers the question. Yeah, good. Thanks, Lyle. Now, where are we? I've written like 100 pages of notes here, hopefully giving the missing information. You've had, I don't know, a couple of weeks. How long have we been gone? 2-3 weeks. To look at, review anything in the gauge theory book, those preliminaries there, and then the added material here. We've been talking about various spin groups. I have lost track. We did SU3, we did SU2, I guess. No, not SU3. We did, I think I defined spin PQ for you.
Professor, sorry, I'm a little slow. I just kind of got the question I was trying to work out for that last problem we have behind you on the board.
Okay, fair enough. What you got?
So wait, sorry, did you just basically say that this left vector is transforming like a dual vector? And is this
Yeah,
H you set up just that you have to modify the dual space? You just have to be careful because there's maybe not the canonical association going on.
Yeah, that's right. So this psi bar really is a dual vector. It's really H lowering the index on the dagger. Maybe from the other side. Well, it's going to be symmetric, so that's okay. And it's Hermitian, so that's okay. But basically, this is what we actually mean by psi bar. Pick up a random quantum field theory book, and they will write psi bar as psi dagger gamma 0. No accounting for taste, But yes, that's the dual vector exactly. I need to know what you guys have covered and what you still need me to talk about. Anything in chapter 2 is something that we'd really like to all be on the same page on before we actually try to quantize a field. So let's, that's a long chapter. Geez, let's see. How long does it go here? From page 35 to page 91. Okay, 60-page chapter. That's substantial. There are a lot of different ideas in there. Okay, special relativity. I think you guys have special relativity down pretty well.
Which book are you referring to when you say
I'm looking
chapter
at the
2?
quantum field theory book. You'll find preliminaries talking about Well, for example, special relativity. If you're like really rusty on special relativity, go to the gauge theory book. But if you feel comfortable with special relativity, what I have in the preliminaries of the quantum field theory book, I've only got 2 topics: Lorentz invariant tensors and discrete. No, discrete Lorentz transformations. So I talk about parity and time reversal and chronicity there. Chronicity is a reversal of the sign of the 4th component of a 4 vector, of the time component. Lorentz invariant tensors, what are they? Anybody? There are 2.
Boosts
The
and
metric.
The metric, certainly, that defines Lorentz transformations, right? What's the other? I don't think I heard it.
Is it the stress energy?
No, that is Lorentz covariant, right? It changes linearly and homogeneously under coordinate or basis transformation. Tensors are linear homogeneous objects, but invariant means you do a Lorentz transformation and it doesn't change. And this is obviously true of the metric, because we can define a Lorentz transformation as one that leaves eta invariant. That's the invariance of eta under Lorentz transformation. But that's a rare property. Most tensors, the components shuffle, any linear equation still holds. But there's one more that's Lorentz invariant. Yeah.
Levi-Civita tensor.
yeah.
Sorry, what?
Levi-Civita tensor.
Levi-Civita, yeah, that's it. And that's not too hard to see if we do it quickly. Yeah, all right, in flat space-time, A, B, C, D. And if I put a lambda A, E, lambda B, F, lambda C, G, lambda D, H on that, this has to be anti-symmetric. So this has to be proportional to Levi-Civita again. Is it Civita or Civita? I've never learned enough Italian to know. But this coefficient is the determinant of that matrix. So if we're dealing with a proper orthochronous Lorentz transformation, the determinant is 1, and that lambda is 1, and Levi-Civita is invariant. All right, now the exceptions to that are like parity and chronicity, and those actually have negative determinant. In particular, parity is very sensitive, exactly sensitive, in fact, to the number of Levi-Civita tensors you have in an expression. If you have an even number, it's even parity. If you have an odd number, it's odd parity, because this actually changes sign under parity. That's a useful thing to know. The other really useful thing to know with the Levi-Civita is if I have 2 of them together, egad. But this is always proportional to Kroneckers. Got to be totally anti-symmetric, and anti-symmetrized products of Kroneckers are often written as a single multi-index Kronecker, E, F, G, H, A, B, C, like this. It's possible there's a sign or a factor here depending on what all your conventions are. In particular, there's probably a minus sign here because in space-time, raising all 4 indices, they're all 4 are different. So you're going to have an eta 1, 1, an eta 2, 2, an eta 3, 3, and an eta 0, 0, which is -1. So the signature comes into raising these, and you end up with a minus sign. But other than that, an even number of Levi-Civita tensors can always be recast as Kroneckers, or if you lower some indices, you'll have some metrics in here, some Minkowski metrics in there. But you can always do that. You can always get rid of an even number. If you have an odd number, the expression violates parity, which isn't necessarily a sin, but there you are. Have we talked about Casimir operators? Oh, all right, let's talk about Casimir operators. Might as well just work through here and quickly touch all the bases. Have you guys read all this? Where are you in your reading?
I'm looking at, I still got the spin groups. That's what I'm reading on right now. All spin groups with the Lie algebra.
Yeah, okay, good. And yeah, I think that's where what we were talking about last time, the spin groups. Yeah. And yeah, we'll come back to that. I wanna do a little cleanup here. So let me work up to that, just touching on various things. Casimir operators are important for field theory. So let's understand a bit what they are. If you have a Lie algebra, you've got, well, n generators for an n-dimensional Lie algebra. So for SO3, for example, the rotation group, the orthogonal transformations, there are 3 generators. It's a 3-dimensional Lie group, and you get a 3-dimensional Lie algebra, a vector space with a basis given by your choice of the 3 generators. Now, there's what's called a free algebra. A free algebra, if you've got like a bunch of things, you can take all products of them, assuming they're things that you have some notion of multiplication for, which we do for matrices. So a linear representation of a Lie group has matrices for generators, because it's matrices that preserve linear relationships. So we can multiply those matrices. So we can form the free algebra of the generators. All right, well, that contains like all kinds of stuff, most of which we aren't interested in, but there can be a few elements of that free algebra, products of your generators, that commute with all the generators. So here's an example. I just got a phishing spam. Let's look at the generators of SO3. You can do it in SU2 as well, but let's, SO3 is fine. So we've got these 3 anti-symmetric matrices, J sub I. From quantum mechanics, think of J squared. You know, what is that? That's JX squared plus JY squared plus JZ squared. Okay, these things satisfy the Lie algebra JI, JJ equals epsilon I JK, JK. Let me not worry about index position. This is all Euclidean. Up is down and down is up. Okay, so not hard to see that this commutes with everything, because if I take JI with J squared, all right, that's a sum on J. We have JI with JJ like this. Okay, so I'll write the square that way. Now, if you haven't ever seen this identity, prove it. When you have a product like this in a commutator, that's the same as the commutator with the first times the second plus the first times the commutator with the second. And this doesn't depend on these two being the same. This would be A, B, C, and there would still be a like thing. You've probably seen that in some quantum class or other. My pen just rolled away. Okay, so working this out, this is epsilon I, j, k, j, plus j, epsilon I, j, k. So I can write this as epsilon I, j, k times, this is j, j, this is j, k. That's the anti-commutator of jk with jj. But most importantly, it's symmetric. This is the anti-commutator, symmetric in jk, and I'm contracting it fully with an anti-symmetric object. So this is identically 0. And that proves that j squared commutes with each of the generators of SO3. That's the property of a Casimir operator. A Casimir operator is an element of the free algebra that commutes with all of the generators. And what that means is that Casimir operators are group invariant objects. Since it commutes with all the generators, the group has no effect on it. And that's really important when we're talking about something like, say, the rotation group or the Lorentz group. So this sum of squares leads in quantum mechanics to the quantum number j. So, you have j plus 1 states in a system with angular momentum j. You've seen this sort of thing, I think. And that's conserved. If you apply rotation transformations, it'll change m but not j. We label states by j and m. M is like a component in the z direction. If you do a rotation, that changes, but the magnitude of that vector doesn't. And that's what j squared is referring to. It's the magnitude of the total angular momentum vector. That is rotationally invariant. Now, in the Lorentz group, there are 2 Casimir operators. And they're, let's write them down and think about them. This is important because this is how we're going to classify quantum states in field theory. So for the Lorentz, we have, actually, let's see, what do I want? Let's talk about Poincare. The Poincare group has generators, rotations, and translations. Okay, so we take the Lorentz group. All right. So M will preserve space-time vector length. P and M will preserve the infinitesimal line element. All right. So X goes to X plus A, but DX stays the same. So translations will preserve the infinitesimal line element. Now, the Casimirs here, one of them that commutes with everything is PA. Now, the Lie algebra here, right? The M's satisfy the usual SOPQ Lie algebra. They come back to M's. It's a subgroup. I won't write it all out right now, but then an M with a P, P is some sort of vector, so it's going to do this infinitesimal rotation. In fact, it's A to B C, A minus eta delta B. Just it's anti-symmetrizing AB here, but it comes into it's linear in P. And then the P's all commute. You know that translations commute. So this is the Lie algebra of the Poincare group. Now, we know that rotations are boosts here, actually. Lorentz transformations preserve the magnitude of 4 vectors. So we shouldn't be surprised that the magnitude of P is rotationally invariant. It also commutes with the P's because the P's commute with the P's. So this is a Casimir. Now, what does it correspond to? Well, we know that we do a boost, and we can write the form momentum as something like m times the 4 velocity. So that magnitude PA is minus m squared c squared. Basically, this Casimir is telling us that the Lorentz group respects masses. And so we can label our quantum field theory states by mass. We expect perhaps some mass spectrum, but the fact that this is a Casimir says we can use M to describe states. The second Casimir of the Poincare group is based on a vector W, which is, let me write it, epsilon A, B, C, D, P, A, M, C, D, up to some multiple. Now, what I claim is invariant is W squared. So W squared is another Casimir operator of the Poincare group. Now, let's figure out what that one corresponds to. Let me move over here. So WA, let's boost the form momentum. So we have C 0, 0, 0. We can find a Lorentz frame where the form momentum takes that form. So essentially, this is going to pluck out the 0 component. I'm going to get MC times an epsilon A 0 CD. Well, that tells us that this vector is space-like. So that's if A is 0, 1, 2, 3, which I can write as 0 or I, going later in the alphabet. Do any of you remember old Fortran? Any of you remember Fortran? I mean, you're using, Python. I don't know what you guys use now. But in Fortran, way back when, if you had an integer variable, you could declare it to be integer by making the name start with any letter I, J, K, L, M, N. Any of those. If a variable name started with anything else, it was a real variable. So real versus integer variables, you still declare those in computers sometimes. So I've gotten used to that convention, right? I think of IJKLMN as a different alphabet than the other letters. So often you'll see I've chosen A to run over one range and IJK to run over some other range, usually spatial. So just a heads up on that one. So I know this is going to be a spatial vector of some sort. It's got, all right, this is constant. So what do we have? I0, CD, MCD. But now what is this? These have to be spatial too. So in fact, this is equivalent, the 4-dimensional one, if you fix 1 to be 0, is, I need a minus sign here to flip those two. But now this is the same as epsilon I, JK, M, JK. Let's see, but that had a minus sign, so that becomes a plus again. But now these M's generate rotations. In fact, this quantity is just twice ji. Right? These are the j's, and w squared is j squared. So our invariants are m squared and j squared. We can characterize quantum fields by values of mass and total angular momentum. And that's just what we're going to do. Now,
Dr. Wheeler?
yeah, question?
Yeah, by definition, do Casimir operators, are they always constructed out of the operators of the group that they commute with? It couldn't be something else introduced. Does that even make sense what I just asked? Because all the examples you just gave us, they come out of the operators of the group that they're commuting.
Yeah, that's
It's
the point of a Casimir, is that it's from the free algebra of the Lie algebra. So they're always built out of products of the generators, right? An n-dimensional group could have several of them. I'm not sure what, there's probably a rule there, but I don't know what it is. I know there are two for the conformal group, one for the rotation group, and there are, I believe, three for the conformal group. So the number does go up with higher dimensional groups. Now, if there's something completely outside of the group, then you probably have some other symmetry going on, and the overall symmetry of your system is a direct product of two Lie groups, and this Lie group doesn't know about that Lie group, so yeah, it'll commute. That'll be fine. I think that's getting at what you were thinking about. Good. Okay, so then, let's see, right? This lets us label groups. And then the next section of these notes goes through a proof, a derivation of all representations of the rotation group. So what we do is we dig into J a little bit more. So basically what we're after, you know, we have the Pauli matrices. If I can replace them by, you know, properly anti-Hermitian things. A convenient choice is I/2 Pauli matrices, Pauli matrix minus I/2 Pauli matrix. And I like to call those tau, because I like to call them tau. And those satisfy the same relation as the J's with real structure constants, epsilon ijk, tau k. You know, the Pauli matrices, you've got a 2i epsilon ijk, sigma k. So real structure constants lets you do geometry with these things. Properly speaking, a Lie group has real structure constants. So to avoid confusion, I always put in there. If I want to find an element of, so these generate SO3, or I'm sorry, SU2. The J's satisfy the same relationship. And in fact, anything that justifies the name rotation group satisfies that same Lie algebra commutation relationship. That is defining of the rotation group. So what we want to find, okay, these are two representations. This is a two-dimensional representation. The J's are a three-dimensional representation. The representation, properly speaking, is a two-dimensional vector space or a three-dimensional vector space. We would like to find all representations. And it's a longer calculation than I should take time to do here. You should just take time to read it in the notes. But let me set it up for you. And you may remember seeing it in some quantum course or some quantum book. We know we have J squared as a Casimir operator. We know that there exists a two-dimensional representation of the group. So, you know, of the possible generators, we can diagonalize exactly one more. All right, this is a diagonal operator. In fact, it's proportional to the identity. We typically diagonalize sigma z, right? We choose the z component to diagonalize. We could choose any one, rotate things and diagonalize it, but we're not going to be able to diagonalize anything more than those two. So thinking back to quantum mechanics, you want to label states by a maximally commuting set of observables. Well, we've just argued we can only diagonalize two. So we can quantize states, or the vectors that these guys act on, with two numbers where j squared pulls out alpha, and we can simultaneously diagonalize jz and pull out another number. So we should be able to label all representations of the rotation group by two numbers, the eigenvalues of j squared, the eigenvalues of jz. What we do with the other two operators is to define j plus or minus equal to j x plus or minus I j y. And now let's call them x and y. This is just quantum mechanics. These are raising and lowering operators. Are these familiar to you? Have you guys worked with these before? Yeah, okay. So let's see, we're in the mid 40s here page-wise. A maximal set of commuting observables, raising and lowering operators. Those notes, you can breeze through those. They just run through what all of these operators do to these states. And it turns out that, okay, we label them by two numbers, which are most conveniently called j and m. By the time you prove that there are limited ranges on these variables and they take half integer values, you show that j squared on a state we're labeling by jm gives j plus a half h bar squared jm, and that jz acting on a jm state gives m h bar jm. So these are code for those eigenvalues. Fine, we all know what those mean. The states then can take, let's see, now we can find out the dimension of these vector spaces. We know that the dimension of Jm, all right, M runs from minus j plus 1 all the way up to j. So you have numbers 1 to j, minus 1 to minus j, plus 0 is 2j plus 1. This describes a 2j plus 1 dimensional vector. J, one goes on to prove, can take values 0, 1/2, 1, and so on. So any half integer value can be taken on by the j's. The odd half integer values are spinors of some sort. All right, that gives a 2. Right, j equals a half gives 2 times a half plus 1. What is that? That's a 3-dimensional representation. Yeah, SU2 is a 3-dimensional group. No, wait a minute. What's wrong? 0 is a 1-dimensional group. Oh, 2 times a half is 1, not 2. All right. Okay, so 2j plus 1 for j plus a half is 2. That gives a 2-dimensional group. You know, this really baffled Stern and Gerlach. Stern and Gerlach were trying to show this 2j plus 1 relationship for some atom, and they didn't know about spin. And they showed that when they do they put an inhomogeneous magnetic field on an atom, they get 5 dots if it's has an angular momentum of 2, or 3 dots if it has an angular momentum of 1. But sometimes they saw 2 dots or 4 dots. They saw an even number of states. And I think it was Uhlebeck and Goodschmidt realized that meant that there was intrinsic spin to the electron. It was a thing that evolved. Those of you taking quantum, I hope you read that Goodschmidt paper. We'll be talking about spin in there. The rest of you are welcome to join, by the way. But these then are all the possible values of J. So now back to the Poincare group and how we classify fields. So M lets us look into the detailed orientation within those vector spaces, gives us a convenient way to look at the different vectors within the representation. But now we're going to classify states by their mass and their total spin. Let me write this as mc squared so we don't confuse it with that m. That's a mass. Okay, so these are now our states, and when J equals 0, we call it a scalar field. That's like your Klein-Gordon field. You guys have seen these fields. Okay, when J equals a half, that's a Dirac spinner, right? Or we call it a spinner. And I like to use letters like psi and chi for spinners, just because I've come to associate certain letters with certain things, and it's a language of my own. What can you say? What's J equal 1? It's a vector particle. All right, J equal 1, 2J plus 1 is 3. So we're talking about 3-dimensional objects here, like normal spatial vectors, only we're in space-time. A typical example would be E and M, right? The vector potential is a vector particle, right? It has spin 1. Haven't gotten anything you guys don't know yet. How about 3/2? Anybody know what a 3/2 field is called? Rorita Schwinger. This is going to be something that has a space-time and a spinner index. So these guys might have spinner indices on them. This might have a vector. This has a vector index and a spinner index. So it'll transform as a spin 3/2 object. Anybody know a spin 2 object?
Graviton.
Yeah, you better know that one, graviton. Okay. Never been seen. Everybody knows it's there. Well, hey, it's tiny, right? Yeah, G, a combination of G and Planck's constant is a really little number. So, but we're under no illusions. The argument that made Dirac keen to couple to quantize the electromagnetic field makes everyone these days, the same argument makes us eager to quantize gravity, because it's these other fields that provide the source for gravity. And if those are quantized, then the gravitational field must be. More concretely, in the Einstein equation, the energy tensor, the source for gravity, becomes an operator. You can't have the Einstein tensor equals some operator. The Einstein tensor better be an operator too, or the equation doesn't make sense. So at some level, we expect there to be quanta, gravitational quanta, and we can conjecture as to what they might do. We can even describe them by linearizing general relativity and quantizing the resulting spin 2 field. Yeah, was there a question, Guillermo? Or are you quantizing the field?
No,
Or
I'm not
your
quantizing
hand
it. No,
was-
I do have a question.
Yeah,
Why
sure.
is it that we only go up to spin 2? Why doesn't it keep going? Like, what's our limiting factor?
We've never seen any more.
But
There
we've
are,
never seen the graviton.
yeah, but we do see gravity, and gravity, the metric is a spin 2 field. It's just, we don't have to quantize to know whether we see them or not. It's a classical spin 2 field. Spin is not a quantum thing. Spin is a property of the rotation group. The rotation group existed, long before the 20th century. So while it's really only at the quantum level that we see half integer spin, it's not, we might have. There's classical supersymmetry. There are some really fun little papers where people have supersymmetrized classical field theories like E&M or something. You can have classical spin. It's just we don't happen to see that in nature. So no question that the graviton is a spin 2 field. It takes 2 Lorentz transformation matrices to transform it, local Lorentz, let's say. So we know what its properties are under rotations. This is all the further we go. There have been papers like Deser has worked on this quite a bit, where he's tried to argue that higher spin fields are actually inconsistent in field theory for this or that reason. And that may be, although there are ways around it. By the time you put a bunch of reasonable quantum field theory constraints, you like unitarity and properties like that, it gets harder and harder to make consistent higher spin theories. In fact, one of the strongest arguments in favor of supersymmetry, which mixes these different fields, is a symmetry that turns, adds a little bit of one of these to the next one and so on. Regis-Schwinger fields are not always consistent. There's actually a consistency condition that you have to add to a simple wave equation type field theory for a spin 3/2 field. There's an additional consistency condition to make it work with normal things like, perhaps have some normal energy condition, something like that. The thing is that if you supersymmetrize gravity, you're going to introduce a gravitino, which will be a Rita-Schwinger field. That constraint is automatic in supersymmetry. Supersymmetry already knows about the constraint that's necessary for Rita-Schwinger fields. The gauge freedom of the supersymmetry actually imposes it. It's like, magic. Like, how did that happen? So, that's one reason people were working very hard on supergravity way back in the late 70s, before everybody started doing string theory. People were doing supergravity theories where a field of each of these types was part of a supersymmetric multiplet. So maybe there are spin 5/2 fields, spin 3 fields, and so on. Making them consistent, there will be some hurdles. Even with a scalar field, if you try and couple a scalar field to general relativity, several people did this, and it turns out that the energy tensor is not always classically consistent. That some observers will see the local forward momentum of the field as being space-like, not time-like. And there was a theory from the 60s, I think, Brand's-Dicke theory, that looked at coupling a scalar field to general relativity. Basically, what they took was the most general coupling of a scalar field that gave the right energy conditions that was actually consistent with the usual classical energy conditions. A lot of work went into testing that theory, and there's, the coupling parameter had to be so small that they just gave up. There's no actual evidence that that scalar field exists. People are always adding scalar fields to general relativity in order to get inflation. People added dilaton. It's an easy thing to fold in and look at the effects of. And so if you need some novel effect such as inflation in cosmology, a little bit of tuning with the right kind of a field coupling can do it. It's amazing how much can be done by writing an action, right? Just knowing the action for a theory, you already know the kinds of interactions that occur, and you can make a lot of predictions right away. Okay, so back to the main story here. We're going to be looking at the quantum theory of, well, the first three of these, because the only consistent quantization of gravity I know is, probably string theory, because, for algebraic reasons. String theory starts off very simply, as instead of quantizing a particle, you quantize a continuum of particles. Same way, canonical quantization of a little piece of string. And you find that those strings, you put in an interaction that let them break apart or rejoin, and you can form loops of string. And those loops of string have spin 2. And so Green and Schwartz thought, well, this is going to be a great theory of gravity. And in the mid-70s, they showed that, in fact, the low energy quantum theory of the spin 2 modes actually reproduces the action for general relativity. The thing that I find very compelling about string theory, when you look at the string modes, right, you get a Fourier series, right? You get a discrete Fourier series for how a bit of string this long can oscillate. And so you write out that solution. You write out, okay, the string position is some x plus some overall velocity plus this whole Fourier series of oscillations of the string. And now you quantize it. And as we'll see when we get to canonical quantization, the mode amplitudes become operators. Fields become operators in quantum field theory. And in particular, each of those mode amplitudes becomes an operator. So you have this whole Virasoro algebra of operators. Now, it turns out, quite remarkably, that in the right number of dimensions, you can build quadratic, here's the free algebra again, you can build quadratic products of those operators. Certain quadratic combinations of those mode amplitudes give you operators that satisfy the Poincare algebra. What that means is that among the representations of the quantum string algebra, you have representations of the Poincare group and therefore general relativity. So to the degree that quantizing this bit of string, like quantizing a particle, is a consistent quantum theory, string theory gives a consistent quantum gravity theory. And it happens at that algebraic level. And I don't know of another system that does that, which isn't to say there's not another system that does it, but it's pretty rare. People have tried a lot of ways of quantizing gravity, and string is very promising. But I don't think we're going to quantize string this semester. We might come back to it and look at it a little bit later on, but this hinges on you guys keeping up with the reading and the problems and the exercises and quantizing everything else inside first. So let's set our sights on QED, shall we? So we have all these various fields, and that brings me in the book up to page 53, where I have this little chart. And I think, let's see, what's next? Noether's theorem. Now, you guys got that from Charlie, didn't you? You guys know Noether's theorem. So, all right, read about it in my notes, read about it in Charlie's notes. But there's this long section, the section 2.5.5, no, 0.4, what you do with an asymmetric stress energy tensor. Don't ever derive one. I mean, if you apply Noether's theorem, right, to find the the concomitant symmetry of what is it? Translation symmetry of the action gives you conservation of energy and momentum, and stresses in materials contain energy. You can do work releasing those stresses, so there's energy there. Another prescription leads you to an asymmetric tensor to characterize the energy, and it does. It's divergence free and fine, but just vary the metric. Make it coordinate invariant and vary the metric. That will give you a symmetric stress energy tensor, right? Don't mess with this, oh, I can add this anti-symmetric divergence thing that is divergence free because I've anti-symmetrized derivatives, and yeah, you can do that, and you can make it symmetric, and you'll end up with the thing you get if you just vary the metric. So I recommend that for finding stress energy tensors. So aside from that, okay, I run through translation, Lorentz invariance, and you get this, you get something like the integral of x times the stress energy tensor. That's an angular momentum conservation thing. And that brings us back to spin groups, which we've already spent a fair amount of time on. So now you catch me up. Where did we leave off with spin groups? I think we looked at SU2 and SL2C. We wrote down the Clifford algebra for Dirac spinners, and that works for, yeah, okay. So what I haven't done, and maybe I should do, I don't know, this gets long, but let me say this. Okay, generators for SOPQ. Yields generators, remember, anti-symmetric. Okay, when the generators, if they're doubly covariant, are always anti-symmetric. And when you turn them into operators, that brings in the signature. Oops. So it's raising that index to make it a proper transformation matrix that will change some of the generators to symmetric and therefore generate boosts instead of rotations. Anti-symmetric things generate rotations. So you get the Q from this. Now, it's convenient to label these things, to just write all anti-symmetric matrices. So here's a way to write all anti-symmetric matrices. I have a bunch of them, right, for every plane. So think of these as anti-symmetric, and if that's 1, 2, I'm rotating in the 1, 2 plane, and I can build an anti-symmetric thing just by anti-symmetrizing something like this. And maybe I want some normalization on there, maybe not. It just depends on how you like to write your Lie algebra. The Lie commutators are nonlinear, so you can normalize them any way you want. That'll rescale your structure constants. So then I can raise and lower these labels as well as raising and lowering those indices. So I can lower B and I can raise C, but basically, if I have M12, that's some big matrix that is anti-symmetric in the 1, 2 components and 0 everywhere else. That's what I built here. One of those is 1, one of those is -1 in the AB positions. So then you find the commutators of these guys and write the Lie algebra of SOPQ. The Lie algebra is written with lowercase letters, by the way. So this is the group, that's the algebra. Then the commutators, the thing about commutation relations is that they are relationships between the generators. You may use these components to derive the commutation relations because you've got to multiply these matrices together. But in the end, you can erase those and write just a relationship between a rotation of the AB plane and a rotation of the CD plane. And I'm trying to think which way I want to write this. I'll just do it this way. There's an arbitrary constant here because I can rescale these guys. But what you get is A to BC MAD. And it's got to be anti-symmetric on AB and on CD. So just do that over here and you'll get the right thing. So A to BD MAC, then anti-symmetrize AB, and I get A to AC MBD. Then anti-symmetrize both, and I get A to AD MBC. And up to that normalization, which I think I like to take to be -1/2 because it makes the Maurer-Cartan equations nice. That is the Lie algebra of SOPQ. Now, whoa. Looks like Eli dropped off the face of the earth here. Welcome back, Eli.
Yep. Technical difficulties there. So
yeah, it happens. Okay, so that's the Lie algebra. You can use any representation to get the Lie algebra. So those chroniclers work as well as anything, and they're easy to work with. I can raise and lower any of the labels here. If I call this MEF and put a bunch of chroniclers here, I can extract an overall MEF, and the thing that multiplies it is the structure constants. So, so this gives me the structure constants, and that lets me proceed further with, well, never mind the Maurer-Cartan equations today. Now, spin PQ. We start with gamma matrices satisfying the Clifford algebra. And from those, we form the commutator. I suspect I'd put a quarter here as a normalization. Right. Mostly I choose my normalizations for gravitational purposes. So you can normalize these any way you like. But the showing that this Clifford algebra really gives me a representation of the PQ rotation group is a matter of showing that the commutators of these guys, CD, equals the right thing, equals something that looks like this. And let's see, given that we've got 6 minutes left, I don't have time to do that, but there are some tricks because these are anti-symmetric. So I can write sigma AB for A not equal to B. I can just write it as gamma A gamma B times a half, right? Because gamma B gamma A is minus gamma A gamma B. The commutator just gives me 2 of them, and as long as I remember that A is not equal to B, all I have to look at is this. So when I do this commutator, I have gamma A, gamma B, gamma C, gamma D, minus gamma C, gamma D, gamma A, gamma B. And so here's what you do. One at a time, you move A to the front, then you move B to the front, using the fundamental anti-commutator. So at the next stage, this takes quite a few lines to do. It's all in the book, but so I can write, let's see, I can move one of these. So I have gamma C, then gamma D, gamma A. Remember, A is not equal to B, C is not equal to D, but A could equal D, C could equal D, B could equal D. So this is going to be minus gamma A, gamma D, plus twice A to AD if they happen to be the same, gamma B. So I can gradually move A to the front. Then I gradually move B to the front. And then the terms with 4 gammas cancel and I'm left with stuff with 2 gammas. The stuff with 2 gammas can be reassembled into sigmas. And lo and behold, you carefully arrange indices and cancel things out. It turns into this with sigmas here. So read it. Okay, that is in, let's see, well, section 2.6.4, I would say. We get that proof. You know, it's not hard. If I had 15 minutes, I could probably work it out right here. But it's written down there. So read it through, just check the steps, or just do it yourself, right? You know, treat it as an exercise and compute that in the algebra and see how the things fall out. You get some eta terms that cancel by the time you get everything back in terms of sigmas. So watch for that. What this shows is that the Dirac matrices do give us a representation of the, a spin representation of the SOPQ, or in particular, the Lorentz group. Now, the fact that it's a 2-to-1 representation comes from the fact that right, these guys act on 2 to the n over 2 dimensional spinners. However, if I take the gamma matrices, gamma A, and I sandwich them between psi and psi dagger, and I need an H here. Basically, what H does is corrects for the signature. You know, that's just a delta if you're in a Euclidean space. But in general, you make this up out of all of the all Q of the time-like generators. But this object, let's call this VA and look at its dagger. That's going to be psi dagger here, then gamma A dagger, then H dagger, then psi. And H dagger is chosen so that, right, some of the gammas are Hermitian and some are anti-Hermitian. And H dagger is chosen to be the Hermitian ones, so that when this gives a negative sign, commuting the H back corrects it. So H is chosen so that this is psi dagger H gamma A psi. And in the notes, I've specified what you need to choose H to be for any even dimension and any PQ. So that all spin groups section, I got swirled into figuring out what H needed to be regardless. And for Dirac matrices in space-time, it basically has to have the same form as gamma 0. So let me show this for Dirac. So back in 4 dimensions, if I have psi dagger gamma 0, gamma A psi with gamma I dagger anti-Hermitian and gamma 0 Hermitian, then here's the reality condition. VA dagger is, all right, psi dagger, gamma A dagger, gamma 0 dagger, psi. So VI dagger, the spatial ones, this is going to be minus. This is psi dagger minus gamma I, gamma 0 psi. But now you commute this back and you get psi dagger gamma 0 gamma I psi. For the time-like one, psi dagger, this is Hermitian. I have gamma 0, that's Hermitian gamma 0 psi. You don't have to commute them. That's already the thing you want. So by putting the time-like ones for H, the Hermitian ones for H that anti-commute with the space-like ones and don't have to commute with themselves, that works. So I run through that in general, and it was kind of fun. But here's the conclusion. This V with the right choice of H is real. That's how you represent an n vector, a real n vector, using spinners. So now, how does it transform? Well, psi transforms under an exponential of the sigma ABs, right? That's our Lorentz transformation. We have 2 psi's here, so we're going to get 2 of them. That's the 2-to-1 correspondence between spin DQ and SLPQ, right? The fact that a real n vector is a bispinner combination means that it's going to take 2 e to the linear combination of sigma ABs to rotate this once. And you work it out, you get double angle formulas, right? And so that means that rotating a spinner, it's easy to see that rotating a spinner by 2 pi actually turns it to minus the spinner. But minus the spinner here and here give the same vector. So this vector already comes back under 2 pi, whereas the spinner is only halfway. And this happens no matter what dimension we're in, no matter what SLPQ we're dealing with. As long as we have a suitable H, there are issues in odd dimensions, but I didn't want to get into that. We can write real n vectors as basically second order representations of our spinners. So yeah, finish reading chapter 2 for Wednesday, or come with questions. Let's see, I think, well, I can say a little more about the Dirac equation, but then I think very shortly we are ready to launch into canonical quantization, and we can start quantizing each of these different kinds of fields we identified: scalar, spinner, and vector fields. So we're getting down to it here, pretty close. Any questions? Anybody? You good?
Yeah, this is
So-
a bit of a stretch, but it connects to the front part, I guess, to the first
So-
question we had in the class today. Does that is this like the 2 pi covering is something like after 2 pi you're rotating the vector into its dual vector?
No, after a 2 pi rotation, the vector comes back to its original self.
But
This is a real vector. This is a proper vector, not a pseudo vector.
but then the inner product is the dual inner product. That's what I'm trying to say.
Yeah, this is a dual inner product here. Yeah, this is the inner product of gamma psi with psi dagger. Hermitian inner product. So we basically have, right, H gives us a metric on spinors. So we've got this inner product of chi with psi that I'm defining as HAB, chi dagger A psi B. That's my Hermitian inner product there.
Mhm.
Okay, so yeah, and then you can use H to lower the A to a B. And so that is making a dual vector of it. Now, that doesn't affect the transformations, because if I produce a psi tilde by acting with an SOPQ transformation, some real linear combination of my generators acting on psi, right? This is some big AB matrix acting on psi B. Then psi a dagger is still going to have this transformation, just the conjugate transformation folded in. So in a product like this is, you know, one of these products where I've got a psi here and a gamma psi there. And I'm taking the inner product of those here. The V tilde is going to be psi dagger tilde, psi tilde. And so there are going to be 2 factors of this matrix, you know, plus or minus depending whether that's Hermitian or not. But basically we get 2 copies of this. So the coefficient here comes in twice. And that's what doubles the angle. Okay. You know, do it for SU2, right? And you'll see it there, or, you know, do it for the Lorentz group. You know, those would be good exercises to, you know, get a handle on all this and, you know, practice it a little bit. And yeah, you work it through just for SU2, and you'll see you've got, you know, either some linear combination of the Pauli matrices, you know, I phi over 2 n dot sigma. You know, it helps to write that vector as some unit thing times a parameter. But you know, you work through something like that for the boosts, I think. Right. So let's see. All right. There's no class next Monday. Tell you what. You know. Okay. Read up through the end of chapter 2 and come with questions Wednesday. I'd like to know how many exercises you guys have worked. So make me a list and email it to me. Don't send me the exercises unless you have questions. If you have real questions on how to do some exercise, you know, we'll just work it out together, right? But you know, just show me a list of, you know, things you've worked through. You know, convince me that you're paying attention. Okay, and then you know, either Wednesday if there are no questions, or then the next Wednesday, we'll start quantizing stuff. Okay, great. By the way, Wednesday, we're going out of town for a few days, so I'm going to want to leave right after class this Wednesday. But other than that, yeah, we'll have fun doing quantum field theory. Yeah, I can stay around and ask questions, answer questions, or ask, whatever. All right. See you, Guillermo. Yeah.
Sounds good.
Today,
See you around.
Okay. We'll see you guys.
See you Monday or see you Wednesday.
Okay. Yeah, careful with that cough.
I don't know where that came from either. I must have swallowed something funny.
Oh, okay. Yeah, good.
See
You
you.
good, Alex?
Yeah. See you, Professor.
Okay, I'll see you. Take care.